The course. So far we have revised basics of group theory, ring theory in the last few videos. Today I want to do the final topic of revision before we start Galois theory, and that is fields. Okay, so I want to spend maybe 1 or 2 classes just giving you a basic overview of the field theory that we are going to study. Okay, so we all know what fields are. I recall that definition. So the main examples of fields that I want to talk about today, and these are things that things you should keep in mind, are the following. So we look at the fields of characteristic 0, namely QRC, and fields between them. So I will explain in a minute what I mean by that, but these are fields that are contained, let's say, between Q and R. So these all have characteristic 0. So if you recall from your ring theory and field theory courses, characteristic means, maybe I'll just quickly recall this. Given any ring, and I'll mention again, though this is a standard assumption throughout the course, a ring for us is always commutative with unity. There exists a unique ring homomorphism from Z to R. Okay, the kernel of this, which is which is an ideal of Z, let's say phi is of the form nz for some positive integer n. Then the characteristic of R is defined to be n. Okay, that is the revision. So characteristic is I should not say positive integer, I should say non-negative integer, because kernel could be 0 ideal, right? So n is a non-negative integer, characteristic is that. So if you further know that R is a field, in which case the kernel of, image of this map phi is an integral domain, right? Because the subring of a field is an integral domain. So the kernel will be a prime ideal. So it's either 0 or generated by a prime number. So the characteristic of a field is always 0 or a prime number. Okay, now the other important class of field is Z mod PZ. Let's say P is a prime. Consider Z mod PZ, which we denote by FP and its extensions. So I'm going to recall the main theorem of finite fields later on. So this is characteristic P, right? So this is a finite field in particular. This is a finite field. Its extensions can be infinite, but this class of finite fields is very important for us. Okay, so these are the fields. So I sort of mentioned this in the previous video. So when we study groups, we look at subgroups. This is the object that is often interesting for us, right? So to understand a group, we look at its subgroups. When we study rings, we look at ideals. Subrings are not that interesting in ring theory. So we look at ideals. And when we study fields, we also look at subfields, but unlike in the group case, the ambient ring and subgroups, when you study them, ambient ring is the most important one. Here we study field extensions. So both the bigger field and the smaller field have equal importance. So we look at field extensions. Okay, so this is typically the most important term notation that we use when we study fields or field extensions. So I'll write down all the different kinds of notations I'm going to use. Okay, so what do I mean by any of these symbols? So all these mean F and K are fields and F is contained in K. Okay, so to illustrate that, we write any of these symbols. For example, we write Q R over Q or C over R. Okay, and Q root 2 over Q, etc. Okay, so or F4 over F2. So this is a field of order 2. This is a field of order 4. Okay, so these are all examples of field extensions, which is the primary object that we study in field theory, and in fact that is a primary object that we are going to study in this course on Galois theory as well. Okay, so let me just quickly recall some of the fundamental things about this. So let K over F be a field extension, by which I mean, as I indicated here, K and F are fields and F is contained in K. The one in bottom is the smaller one, the one above is the bigger one. And let alpha be an element of the bigger field. Then we define two important things. So F square bracket alpha is the smallest subring of K containing both F and alpha. Okay, and the other important subring, it is in fact a field, is F round bracket alpha. It is the smallest subfield of K containing both F and alpha. Okay, so these are two important things. So we have always this chain of inclusions. So you have F square bracket alpha and contains F round bracket alpha, because if F square bracket alpha is the smallest subring containing F and alpha, F round bracket alpha is the smallest subfield, so it's also a ring. So it contains F square bracket alpha. This one can check. Okay, so any subring of K containing both F and alpha contains F square bracket alpha, and this is clear. Another description of these is the following: F square bracket alpha consists of polynomials in alpha with coefficients in F. Okay, so in other words, it consists of all things of the form an alpha power n, a1 alpha plus a0, ai's are in F, and n is some non-negative integer. Okay, that happens to be a ring. Every ring that contains capital F and small alpha must contain all such polynomials. So, and it happens to be a ring. So this is the smallest subring containing this, and this is the quotient field of F square bracket alpha. Okay, this is in fact ratios of polynomials. So these are F alpha divided by G alpha, where F and G are in capital Fx. So they are single variable polynomials over capital F, and we want G alpha to be non-zero. So this also justifies this chain of inclusions. Now this is very general. What I now want to do is to understand a little bit more about what these subring and subfields are. Okay, now an important definition. So let again K over F be a field extension. everything that you study in field theory starts with some statement like this. Let K over F be a field extension, because field theory is really a study of field extensions. And let alpha be in K. So you have an element in the bigger field. Then alpha is algebraic over F if there exists a polynomial fx in capital Fx such that f alpha is 0. Okay, so we say that alpha is algebraic over F. This entire phrase is important. As we'll see, being algebraic is a statement about the element and the base field. If so, just to complete the definition, if alpha is not algebraic over F, meaning there is no such polynomial which has alpha as a root, then we say alpha is transcendental over F. Okay, so examples: root 2 is algebraic over Q. Take Fx to be x square minus 2. Okay, pi is transcendental over Q. Okay, this is a fact. It requires, it's a theorem in mathematics that there is no algebraic, there is no polynomial over rational numbers which satisfies alpha, which has pi as a root. Okay, so these are important notions for us. So now I am going to write down a series of facts which again you learn. So remember, again, this is not supposed to be an exhaustive revision. I am just listing important facts so that it gives you a way of what kind of things we need from field theory. Okay, so maybe I will just label them like this. 1, if alpha is, so again, maybe I will just make a global assumption. K over F is a field extension, alpha is in F. Sorry, alpha is in K. If you define L to be alpha in K such that alpha is algebraic over F, this is my notation. So we say, we write, for this we write alpha is algebraic over F. Just a shortcut for me so that I don't need to write the full sentence. So if alpha is algebraic over F, you take all such elements. So of course F contains this. Is a subfield. So the statement is that it is a field. This set is a field of K containing K. So we always have, given a field extension, we have L in the middle. So this is the set of algebraic elements over F. Okay, so we say that definition, the field extension itself is algebraic if every alpha in K is algebraic over F. Okay, so so this in particular is an algebraic extension, because everything in L is by definition algebraic over F. So we say it is algebraic. Second fact is, if alpha in K is algebraic over F, then the smallest field containing F and alpha is same as the smallest ring containing F and alpha. Okay, so this is an important fact. So when we are dealing with algebraic elements, we don't distinguish between square bracket and round bracket. So here the idea is that use the polynomial F. I am not going to prove this fact, but I will simply say that use the polynomial Fx which has alpha as a root to show that alpha in F square bracket alpha has an inverse, has a multiplicative inverse. Has a multiplicative inverse, that means it's a unit. Okay, so f square bracket alpha already happens to be a field, so that is what we take. Okay, so now so some other things, these are not facts really, but I'm introducing new things to you. So let suppose alpha in K is algebraic over F. So then I equal to all polynomials in Fx which have alpha as a root is an ideal in Fx. And from the previous videos we know that Fx is a PID, right? Because F is a field, the polynomial ring in one variable over a field is a PID. So I is generated by a single element. And this is called the irreducible polynomial, and that will be irreducible. That is one can that's a fact one can check. It is called the irreducible polynomial of Fx over capital F. Sorry, irreducible polynomial of alpha over capital F. Okay. So I'm going to give examples of all these things. And definition, degree, if so, let suppose alpha in K is algebraic over F, then the degree of alpha I am going to degree sub F. Okay, so maybe I'll first write it in words. Degree of alpha over F, it is denoted, degree sub F of alpha is by definition degree of irreducible polynomial of alpha over F. Okay, so that is the degree. And let me just complete the review and then we will spend some time giving examples. So let's say K over F is a field extension. We can think of, or we can consider K as a vector space over F, right? Because what is an F vector space? F is a field. An F vector space is an abelian group which admits multiplication by F, elements of F, namely scalar multiplication. Of course, K is a field, so it's an abelian group, and you can multiply two elements of K among themselves. So certainly you can multiply an element of K by an element of F. So it is a K vector space. The degree of this field extension denoted by this symbol is dimension of K as a F vector space. Okay, so that is the degree of a field extension. Okay, so I think I have essentially recalled the main things for now that I want to discuss. So let's go ahead and discuss various examples. First one, we know that R over Q is not algebraic. The field extension R over Q is not algebraic. Remember, an algebraic extension is an extension where every element of the bigger field is algebraic over the smaller field. So even if there is one transcendental element, the extension will not be algebraic. So the reason here is pi in the real numbers is transcendental over Q. Okay, so what about C over R? So first let's do C over Q. Is also not algebraic because pi is a complex number also, right? So there is a transcendental element. Whereas C over R is algebraic, right? The reason is C is in fact R square bracket I, which we agree is the same as R round bracket I. In fact, we know that C colon R is just 2, right? So this is the degree of that field extension. So let's now continue. So Q square bracket root 2 is same as Q round bracket root 2, because root 2 is algebraic over Q. So what we have is R Q root 2 Q. And also when I define the degree of a field extension, the terminology is that you put that number here, okay? So on the bar. So for example, here you write C R, and 2 represents the fact that it is degree 2. So this is 2, and this of course is infinite. So every time you have non-algebraic extensions, it's an infinite dimensional vector space. So that is because pi square, pi cubed, pi power 4, pi power 100 and so on. This set is algebraic, is linearly independent over Q, right? That is the meaning of being transcendental. If there is a linear relation, that gives you a polynomial for which pi is a root. So this is infinite dimensional vector spaces. Okay, so similarly this generalizes to Q is algebraic for all n. Okay, so some other examples. If you take zeta n to be a primitive nth root of unity in C, so then that is a algebraic extension. We will learn later what the degree is. If n is prime, the degree is just n minus 1, but otherwise you have to, it's the Euler function, which at some point we will discuss. Okay, so now let's talk about degrees of some specific elements. So I'm going to recall what is degree of I over Q, I being the square root of minus 1, complex square root of one of the square roots of minus 1. Degree is clearly 2 because irreducible polynomial here is x square plus 1. What about degree of root 2 over Q? This is also 2, right? Here the irreducible polynomial is x square minus 2. What is the degree of root 2 over R? I claim this is 1 because x minus root 2 is a polynomial over the base field which satisfies root 2. So the degree of the irreducible polynomial is just 1. So in general, of course, if you have alpha in F, then degree of alpha over F is always 1, right? So degree sort of tells you how far away it is. Okay. If it's degree is a positive number, it's 1 means it's in the field itself. Similarly, degree of I over C is 1. Okay. And the final thing that I want to mention here is the multiplicative property of degree. Okay, this is an important result for us which we constantly use. So this says that let you have K, L, F be field extensions. Then what we have is the degree of K over F. So remember, this means K is a field containing L, L is a field containing F. So the degree of K over F is the product of degree of K over L times the degree of L over F. Okay, and this formula holds even if one of them is infinite. So with the understanding that infinity times any number is infinity. So if K colon F is infinity, if this is infinity, one of these must be infinity. Otherwise, if these are both finite numbers, this is also finite number. So this is most useful to us when everything is a finite extension. and we constantly use this. So, and this tells you, for example, useful, this is very useful, so that is what I am saying, this is very useful. So, for example, let us apply this to the following situation. Show that root 2 is not in Q adjoint fifth root of 2. So, this is a, let us take, this is a fifth root of, there are lots of fifth roots of 2 in C, I take one of them, in fact I can take real fifth root. I claim that root 2 is not there. See, this kind of statement, if you try to do it from first principles, it's a bit tricky because you have to work with arbitrary elements of Q adjoint fifth root of 2, and so that none of them has the property that its square is 2. Whereas if you use the degree, multiplicativity of degree, this becomes very easy, because what is the degree of this extension? What is the irreducible polynomial of fifth root of 2 over Q? This is nothing but x power 5 minus 2. This is because x power 5 minus 2 is a polynomial in Qx which satisfies, which has fifth root of 2 as a root, because if you plug in x equal to fifth root of 2, you get 0, and this is irreducible by Eisenstein criterion, which I recalled last time. So, this is irreducible and it has fifth root of 2 as a unit. It's monic, which usually you take irreducible polynomial to be the monic, because you can always multiply by a scalar, it will be smallest degree polynomial having that as a root. So, you take the monic one. So, this is the irreducible polynomial. That means this degree is 5. Okay, so here there is a fact. So, maybe I will write it here. Fact is, so you have K over F, a given field extension, alpha is algebraic over F, then the degree of F alpha over F is same as degree of alpha over F. Okay, this is a simple fact, you can check this. Okay, so this says that it's 5. Now suppose that root 2 is in Q adjoint 5 root of 2. So then that means you have this field extension, given field extension, but Q adjoint square root 2 is in between. This is 5, this we know is 2, right? That is clear. So whatever this number is, we must have 5 equals 2a, because this is 5 is equal to 2 times a, just directly applying this formula here. But this of course is not possible. So that means this cannot happen. Okay, so as you can see, this is a nice illustration of what we can say about field extensions and the multiplicative property of extension, degrees of extensions of fields. Okay, so let me stop this video here. In the next video, I am going to recall a few more things about fields and talk about finite fields, and then we will be ready to start Galois theory. Thank you.